Uh, is Dr. Shoman there?
Yes, Professor. I'm
Oh,
here.
hello. How are you?
I'm good. I'm good. How are you?
Okay, okay. So, how is the winter here in Kolkata? We have winter here, or in Bolpur we have winter here in Delhi. But what's about that there in Germany?
It's the same here. I'm in my sweats. You can, as you can see now.
Yeah,
So
yeah. I
yeah,
mean,
it's pretty cold.
temperature like?
It's like 5, I think now. Now it's
Oh,
little warmer because it's afternoon over here. So it's around 9. So 9 to 10, around that.
I see, I see, I see. So, Dr. Kundo, have participants joined or are they joining still or something?
Yes, sir.
So you let
Yeah,
us know when to start.
we can start, no problem, sir.
Okay,
Because
okay, fine. So go ahead with your plan then.
okay, sir.
Okay, okay.
So, uh, good evening, everyone, our participants. It is the 5th day of our faculty development program. So, today's topic is optimization in industry 4.0. So, our expert is Dr. Joykishan Soman. So, before that, let me introduce some bioprofile of Dr. Joykishan Soman. He has completed his Bachelor in Mechanical Engineering from MA College, Kottamangalam. And after that, he started his career as a senior engineer in Larsen and Toubro from 2011 to 2013. After that, he's completed his MTech in Industrial Engineering, Masters in Industrial Engineering Management from NIT Trichy, and PhD in Operational Management from Indian Institute of Technology, Bombay. So after that, he has a wide industrial experience. He was a senior manager, Delivery Private Limited. He was a postdoctorate fellow, Norwegian School of Economics. And after that, he was a operation consultant, again in Delivery Private Limited. And now at present, he's working as method optimization specialist in Lufthansa system. So he has a large number of publications, and he has guided master thesis also. So this is the brief profile of Dr. Joykishan Soman. Now, Dr. Soman, the session is yours. You can start now.
Okay. Thank you, Professor Pranav. Pranav, if I'm pronouncing it rightly. Yeah. Thank you. Thank you for that lovely introduction. So, as he said, my name is Jagishan Soman. So, I wanted to take this presentation as much as interactive as it is possible. So, please, I've started by sharing my screen. So, maybe I have not prepared much presentations. I don't want to bore you with a lot of slides. So, you can see my screen. Can you see my screen?
Yes,
Can
yes.
somebody?
Yes, sir,
Yes,
it is.
yes, yes, yes,
Yeah,
yes.
yeah. So as you can see, I have just prepared only 30 slides. I want to bore you with a lot of topics. So, but if you guys are very interesting about my presentation, I have some additional slides, some additional problems also that we can cover because it is kind of 2-hour session. But what I planned was like we will have a basic discussion on different experiences I had with mathematical problems in industries. And let's see how the session goes. If it is not boring for you guys, then we will take it further. Otherwise, we can stop whenever you guys say.
Just would like
So
to
I will
add,
just,
I would like to add,
yeah,
Dr. Shoman, is that according to AICT,
yeah,
each session is for 1.5 hours. So it
okay,
is starting at 6. It will be up to 7:30. So actually, you can close that 7:25 with certain closing remarks that Professor Roy will be making, because next faculty would be appearing at 7:30.
okay,
Yes, sir.
Yeah, yeah,
understood,
yeah, yeah.
understood. Okay, then we will go one So is it like there will be an interaction session or it will be just my presentation? How you have planned it?
You can pose some questions, but I don't see much response here so far. But however, you can always do, and there will be certain questions in the chat box, or maybe some people would be asking one or two questions like that.
Okay.
Yeah.
Okay. Okay, then that is good. So if you guys have any clarifications or if there is anything which I wanted to explain further, please post it in the chat and we can pause and then we can discuss that. So without further ado, I can actually start. Just give me a moment. Let me start the presentation mode. Yeah. Okay, so I titled our talk today as Decision Modeling in Transportation and Logistic Industry. So as Professor Pranav has already mentioned about me, I have worked in quite a few different domains, I can say. So I started my career with Lasman Tubru. So I was mostly in the manufacturing sector, but I was not using that much of mathematical modeling or anything over there. It was primarily resource allocation and like CNC machining and in that domain. So mostly I will be focusing on mathematical tools being used in industry. So I actually made the presentation on transportation, aviation, and warehousing. So I can actually show you. So this is my primary contents for the presentation. So we'll have some case studies from logistics domain, from warehousing, and from aviation. And these topics are being carefully taken. And I'm not going to discuss much further mathematical modeling in it, but rather than the application of mathematical models. So one of the reasons for that is like the mathematical models is copyrighted. So most of these models which I have worked on is currently used by the company, and I cannot actually showcase that in a public forum. But of course, we can discuss about the application. And in general, I don't know the domain structure of the audience here, but I believe most of you are from a research background. So you might be having better academic experience than me, or even industrial experience than me. So I'm all ears for if you have a better better approach or your suggestions. So always that is helpful for us that we discuss about the problems, and if there is alternate approaches, better approaches, definitely that would be kind of a addition to the work we do. And most of the work what I'll be presenting here, we have communicated in some kind of a journal or some kind of a conference. We have communicated that. And also, this is the second presentation of some of the case studies, especially in logistics, which I presented in some other closed room sessions, I can say, with some of the universities in India as well. So it was always been very interactive. So please be free to be more engaging and interactive so that it will be more engaging for me as well. It won't be one way. So for the audience who don't like to actually speak directly, you can directly put it in the chat so that we can take it that as well so that the presentation will be more interesting. So let me go to the first one, logistics. So in logistics, as as I have mentioned, I worked after my PhD, I worked with a company called Delivery. So it is one of the largest e-commerce third-party parcel delivery company in India. And it was kind of during the time of COVID. And why that is important is because it was during this time they had major restructuring of their network, because as you know, during the COVID time there were no that much in the initial peak there was a dip in the demand, and suddenly the online delivery picked it up, and there was a huge demand, huge market fluctuations, high peaks and all. So then what happened was the network became very unbalanced, and they really needed the solutions to cater to the peak demands and all. So that's where the research opportunity appeared. So back then I was working as a research student, maybe, yeah, as working as a research student. Then these questions came to my university, and we formed a research team and actually worked on that. So it was primarily the design of the network, line haul delivery, last mile, and gradually that paid my way into the company, where we actually established in our like operations research division over there, and we worked on similar problems. So just to give you a rough idea what I'm talking about, operations research. Operations research, maybe like many of you guys will be already knowing about this, but operations research is how I define it. It's basically using mathematical models, principles to solve logical problems. So combinatorial problems. It's basically, if it is a small size problem, you can actually logically find an answer. It's always like feasibly, to get a feasible answer, you can actually think of different combinations and find a feasible answer. But using mathematical models like linear programming models, there are constraint programming approaches through which we can actually find a near optimal or a better solution than this logical solution, which a person or like group of people can define. So why I made this definition initially before going to the case studies is, in most of the companies, I have felt like they tackle this problem because it's a logical problem, right? So it's basically how many packages, from what point to what point, how many packages we have to deliver and all. So people tends to control this through like smaller workarounds. Like naturally, you can see that bigger cities like Chennai or like Kolkata, Delhi and all, it will be having enough demand that one can actually plan the number of vehicles or the trucks which is required for the delivery. But once the size of the problem becomes larger, I remember when we started tackling these problems, they had around the large capacity centers like 100, 200 around large capacity centers. But now it has close to 1,000. So that is how the development actually happened. It was just been, I think, 4 years, 5 years now, but within 5 years it grew like that. So logical models, handling them through mathematical approaches, always has that advantage of getting better solutions, which is very hard to find otherwise. And another point it is, we are using mathematical models as an optimization tool. There are other approaches like machine learning, artificial intelligence. It will give you a workable solution, but in some point, this workable solution may not be enough. We want to get an optimal solution or near optimal solution, which can which actually translates to a lot of savings for the company. We will come to that in one of the case studies, but I will start with the first one. So yeah, so just to give you an introduction to what type of a system we are talking about, I have just included 1 or 2 slides about what is a network construct in a parcel delivery company. So it's primarily divided into 4, as you can see. So there will be a first mile. Okay, where is my laser pointer? Yeah. So you can see there will be first mile, and then there will be a primary line haul, secondary line haul, and a last mile delivery. So the first mile delivery is basically like, picking up the collection point. So it's basically it's a first starting point. So I will start it with a normal example. Like for example, you consider an Amazon, how you make an order in an Amazon. So if you ask for, say for example, you are ordering for a set of books. So there will be a seller who will be selling this. So there will be a collection agent who will be going from a service center or a distribution center to this collection point, and they will actually collect it directly from the center, and then they will actually assimilate it together and gather in this pickup centers. So from the seller directly, the delivery boy or a delivery person will actually collect those books, and it will reach the pickup centers. And from the pickup centers, it will be actually transferred to the next level in the network. So these pickup centers, collection points, and the distribution centers, even though there are different names, the primary purpose is kind of the same, which is the first mile pickup operations, except for this distribution centers and service, because this has dual purposes. Service centers can also be a part in the last mile delivery. same as distribution centers. So the difference between service center and a distribution center was on what type of product or what type of a category we are considering. So for example, books or online delivery, it will be mostly handled by distribution centers because it is a B2C segment, like from the business to directly to the customer. But if you are considering a B2B segment, so for example, if you want to transfer refrigerators, and at that time, we had a huge order of refrigerators from a popular company in India. And there were cars also. So one of the popular country in India wanted to transfer cars from point A to point B. So these demands are not handled by the regular distribution centers or pickup centers. For that, dedicated service centers will be opened. But those service centers sometimes will be catering to one or two customers, like one or two businesses, I can say. It may not be handling to too many people. It will be dedicated for one or two clients or a clientele, I can say. So service centers are specifically for B2B, and distribution centers are for B2C operations. And distribution centers will have both delivery in the last mile and pickup in the first mile, that operation. And pickup and collection points are dedicated for online. So it was basically online, like the books or whatever you are ordering, that for that purposes, collection point and pickup centers were dedicated. So that will come in the first mile aspect. Then if you consider the primary line haul, from primary line haul, it is more structured, I can say, because here this you can actually consider it like the grassroots. Like there are many channels through which you are actually getting these products to the collection centers. And in primary line haul, it is basically between the hubs. So the products which are products or like the packages which are received in the first mile centers, they have to be transferred through IPCs, so or hubs. So what is an IPC is like, it is called as intermediate processing centers. So the word processing center is like, there we actually categorizes these parcels. They categorizes in a way that like the movement through the network is much smoother. Because, for example, if a person from Kolkata is ordering say, he or she is ordering some book from from a seller in Delhi, the book from the Delhi will be coming to the Delhi distribution center or a Delhi pickup center, and from there there will be an IPC over there. I think we have a Guragaon IPC. I think there are 4 or 5 IPCs over there. So the purpose of IPC is like they will process this shipment and then categorize like them into different bigger bags, I can say, and which vehicles it has to be actually routed through. So those decisions will be done in this IPC, the processing centers. So that become the basic starting point of the shipment, I can say, into the line haul network. And as you have seen, it depends on the volume, turnaround time, and the origin destination pair. It will be connected through an intermediate IPC or a hub. So it is like if say you want to have a book or maybe a book, it can wait. I mean, the delivery time will be like 4 to 5 days or maybe even 3 days. That's okay if it has to reach to Kolkata. But say, for example, if you want to have a eyeglasses, which is like high demand item. I mean, the weight is less and but the value is a high value item. So it can be directly airmailed also. So then it can be like point to point. It don't want to get connected between multiple IPCs. So for such items, the turnaround time will be like very less. It has to be directly connected from one IPC to another IPC. So it depends on the destination. It depends on the turnaround time, and also depending on the volume, we decide like whether the shipment has to go through multiple IPCs or directly it can be given to the final IPC or not. So the connections between IPCs will be constituting the primary line haul. And secondary line haul is basically how the shipment is actually transferred from an IPC to the DCs, distribution centers. So there are typically 2 types of mappings. So there is like several DCs is connected to a dedicated IPC. Depending on the geographical proximities and the load transfer characteristics. But this is actually a fundamental difference in how our research papers or like how academics actually have portrayed it in a way, because one-to-one mapping maybe from an academic point of view, it may not be that nice because we can actually, if it has a multiple mappings, then it can be having a better load transfer. So for example, if you are constructing a flow model, in a flow model, the multiple assignments can be more beneficial than an independent dedicated assignment. But in on ground operations, what happens is like sometimes when there are multiple mappings, it will be very troublesome for the actual operations. So in certain locations, we have dedicated IPC markings, which can actually benefit in advantages in operation because of the operation challenges. And in certain other conditions, like lower load areas, several mappings can also be accommodated. So it's basically a hybrid system. So it's not always like one will be connected to the other, but it can also have several mapping, like the DCs can be connected to multiple IPCs as well. So it depends from the load characteristics, but because of the operational convenience, most of the time, one-to-one mapping, many-to-one mapping is what is more favored, I can say. And the last one will be the last mile. So if you ask anybody from a third-party delivery company, I mean, like from a parcel delivery perspective, the highest challenge is coming in the last mile delivery because and this constitute the the highest chunk of money you are paying for a delivery. If you ask me, if you are placing something in Amazon, the amount which you are paying, it's actually going to the last mile delivery. In the distribution cost, I meant it will be going to the last mile because it is very difficult to streamline that, and there will be a lot of uncertainties over there will be delays. There will be returns, and so it is pretty difficult to manage. So in a sentence, I can write like it will be directly a delivery from a distribution center to the or from a service center to the warehouse. But the last mile network can be pretty much challenging. The usual thing is like you can put a worker routing problem like with time windows or like very simple models like daily routes, but dynamic routing problems, etc. But the issue is on ground when it comes to the real time operations, there are so many challenges, there are so many uncertainties which occurs. So we actually designed robust models. We had designed some stochastic models over here to cope up with the uncertainties happening on ground, because last mile is a place where we have to like plug in a lot of there are a lot of loose ends, I can say. So this is a very challenging part for any of the delivery network, I can say. So this is the primary four tiers or the divisions, I can say, for a delivery network. So is there anything to be clarified? Just stop me in between. But is there anything I have to clarify more, or can I move on? Okay, I will take it as an S. So this is very similar to what I have explained before, like how the network behaves. So now we are looking at from a individual parcel or like an individual shipment perspective. So it is very similar to our old example. Like if you are booking a book through Amazon, a person from Kolkata has booked has actually made a booking for a test book from a Delhi seller. It will be reaching the pickup center, then it will go to an origin IPC where it will be processed, and then intermediate IPCs and destination IPC and final to the DC, and then the last mile delivery happens. So here is the first mile delivery, and then between this will be basically the secondary line haul, the IPCs connecting to the IPCs to the pickup center or IPC to the destination centers. This will be basically the secondary line haul, and between the intermediate hubs and origin to intermediate and intermediate to the destination hubs, this will be the primary line haul. So this is just a different view of the same network, but from the perspective of a shipment. So some of the operational research problems we faced. So as you can see in the background, this was one of our initial project. I think it was during the time of COVID, 2020 is that time. We actually implemented a zonal perception, I guess, like how to cluster different points and create a network. It was good for the time, that I should say, but later on we had to change it to a multi-commodity model. But this was one of the approach we did back then. But let me first go through different problems we faced, like different classification of the problems we faced. So it's like mid-mile network optimization, all comes in the network design, last mile delivery solutions, and there will be line haul optimization. So this all we categorize within network design problems. And there was scheduling challenges, like there was route scheduling, vehicle allocation, and this heterogeneous fleet scheduling. So heterogeneous fleet, they have diverse fleet arrangement. You can imagine you might have already got this parcel like e-commerce parcel delivery, even from two-wheelers to three-wheelers to four-wheelers. You have different variants and with different capacity, different cost structure. So handling a heterogeneous vehicle fleet is really a headache. So I remember like when we are looking at into the academic or like to the research being published, we when we have seen the word heterogeneous, but the aspect of it on real life was like totally different. I mean, the way they calculate the cost, for example, like if you open a research paper, you can see there is a fixed cost, there's a variable cost, but those costs are actually estimations. So to arrive at that cost itself require a lot of analysis. Like there will be driver costs, there will be depreciation costs, there will be insurance for the vehicle. And if it is like if you are getting it from a vendor, then there has to be like vendor managements and like what vendor has to be selected for which fleet. So arriving at that fixed cost or the variable cost itself was challenging. So heterogeneous fleet scheduling was a very challenging problem, I can say, especially when considered when wide varieties of vehicle is available, which is common for any parcel delivery network company. It is not only for delivery. If you consider any company, it is a common challenging like how the vendor selection and how to determine these cost factors and how to forecast what will be the future cost inflows and the profit inflows. And route scheduling and vehicle allocation is pretty much straightforward because when you once you design the route, you have to actually see like which vehicle is better suited for the route. And for here also we use mathematical models. Even though you see machine learning back then, AI was not that popular, I can say, but machine learning like reinforcement learning, and so it is also much appreciated. But at the time when there is huge disruptions, right? Like it was not prepared to handle such disruptions. That's where the optimization problems, I mean, the mathematical models had the upper hand. We were able to use our classical models and get a better allocation than the machine learning models, I can say. So just to brief, that was my story with scheduling problems. And then there was warehousing problems. So this warehousing problem actually happened within the company, I can say, within the IPCs, intermediate processing centers, where they have to process and they have to store, like at least temporarily, they have to store somewhere these packages and parcels. So that actually opened up two major problems for that, like sorter bay reassignment, we will cover that, and the bagging assignment for transshipment consolidation. So one thing I would like to specify here is when we are handling such large networks, usually the packages will be consolidated together and only one address will be added to it. It won't be the last address. It is something called as next transfer center. So even if the book which you have ordered, it's from Delhi to Kolkata, but once the book arrives at the pickup center, it will be relabeled. So the next address for that book will be just to go to Delhi IPC. And once it reaches Delhi IPC, it will be just next Kanpur IPC. It won't be like the final destination. So it actually helps the ground operations to be more efficient, I can say. So they don't want to actually look at the last address. They just want to scan. So everything is barcoded. So they just want to scan it. It will just show like, okay, Kanpur, just put it in this bag. So once we visited the warehouses, I mean, IPCs where the sorting actually happens, it is very efficient. And we have to make it in this way because the system or the mathematical model will decide like where the shipment has to be rerouted. But for the people on ground, they just want to scan it and they will say like, okay, they put it in this location where the collection is done for Kolkata, or this location for the collection for Kanpur. So for them, it is just scan and put it at that location. But our assignment was to actually build the models more efficient, that it will actually to route the shipment in a more consolidated and more cost-effective manner. So we will come to the Bay assignment problem. That is my case study with warehousing in a bit. And then there is this classical routing problems. There is worker routing problems. There is with time window, multi-depot, pickup and delivery. So like even backholds was there, then stochastic worker routing problem, dynamic worker routing problems came. So all the variants in worker routing problem is very much critical for such a parcel delivery company. And we have used the standard models, we have used heuristic models, and yeah, and we have developed some in-house algorithms as well for tackling the routing problems. And then there was a location routing problem. Also, we had inventory routing problem as well, so as a different variant. So location routing problem was required because some of our IPCs, we shifted it depending on the seasons and the delivery patterns, sorry, the demand patterns. So if the demand pattern says that, say, for example, in Kolkata, if say in Howrah, there was like, it's better to have an IPC in Howrah because we can consolidate the better. But due to demand shifts, maybe after 1 year or 2 years, there has been more shift in the demand, and it is more beneficial to actually have something at Kharagpur. I know I have visited Kharagpur only once, but I have seen it's little rural, but maybe the model suggests like it is better to have a smaller IPC at Kharagpur and also another smaller IPC at Howrah, rather than have a very big facility at Howrah. Because at Howrah, I can imagine getting a bigger facility over there, you have to invest a lot of money, right? But Kharagpur, it will be little less. So how these decisions can be taken, and for this decision, we have to consider the leasing agreements, we have to consider the cost of operations, we have to consider the routing problems, docking facilities. So it comes as a combined problem. Just by looking at the location or just by looking at the routing, we cannot take informed decisions. So that's where this location routing problem came. And during time of COVID, it was very well required as well, these leasing agreements and opening up newer facilities. So yeah, so that's how that is some of the problems we faced in the routing domain. And so this is so till now, I think you might have been thinking like why I'm saying so much of introduction before coming into the actual case study. So I just wanted to give uh, give an experience of like what is the environment, or what is the place where we are actually introducing such problems. So that was the only reason why I spent this much time on the prayer presentations and then the prayer slides. But here we are going to take a concrete case. We are going to take a concrete problem which we worked on. So it is worker scheduling problem with fixed ETD. So ETD is like estimated time of departure. So this, I can say like this, we had an innovation in which we considered a different modeling approach to tackle the situation than the classical approaches what has been done in the company so far. So I will just explain the problem first. So the freight distribution companies like delivery usually have cyclic schedules combining with different routes, and we call it as something called as route sets. And in the route set, it's like the worker should start from one city and should return back to the same city. It's just like a VRP problem. But the thing is, the worker so it has two aspects. It's not like every worker should return back to the starting city. It may happen that some workers can enter such popular cities. Like for example, if there is a truck starting from Kolkata, the third party contractor which we are leasing the vehicle, they might be okay that if we return it in Delhi. It is very similar with the outstation car business, I can say, but we used it for the truck, but it is very similar. Like you can pick up a car from one location, drive to another location, and you can return it over there. But again, there are many contracts for it. The cost structure is different. But this model we consider for our in-house trucks. So we call it as TT, tractor trailers. So at that time we had, I'm not saying the number, but we had quite a sizable fleet of TT. So these tractor trailers are like 48 feet vehicles of larger capacity, and it is operated completely by the company. So whatever overheads or the fixed costs, everything we have to take care. So for us, the requirement was like the vehicle has to return back to the place where it has been started, because that's the base location for that particular vehicle. The maintenance, everything happens at that base location. So it was a requirement from the operations side that the vehicle should return back to the starting city. So that is the main premise of the problem. And there is always deadheading. So deadheading is something like you may have to shift the vehicle where there won't be any load. So basically the tractor trailers, the tractor will be there, the trailer part will be there. So the trailer may have to actually shift from point to point. But I think we also considered 24 feet trucks as well, not only tractor trailers. So basically, sometimes the vehicle has to move from point A to point B without any load in it. So that will be deadheadings, and it is very costlier. Nobody wants to actually drive the trucks without load in it, so it is lost to the company. So costlier deadheadings are the waiting times were the between the routes. So maybe we can see that in this particular graph. It is basically a time-space network, I can say. So I have just taken an example of like say 6 cities over here, A to F, and the time is given. And you can see different trips. So for example, this orange one, if you see, the trip is from A to D, the city A to city D. And after reaching city D, it is waiting for some period. I mean, it escapes at 8 p.m. at night, 8 p.m. at night at day 2. It waits for 2 hours, then connect from the same city D back to A. So it has become a complete trip. Like it started from A, reached D, and it came back to A. I will say it's a good trip because we just wanted to wait over there for 2 hours. Drivers will be having sufficient rest, or maybe the driver swap will happen. If D is like far away, some other driver will pick up, and then they can drive back. So this application, it's very similar to the train or a long distance bus travel and all. The bus will actually be running, the drivers will be swapped. So similarly, so this is very good route. So it started from A to D and then went back to A. But if you see the green route, right, it has traveled from A to city E and then from E to F. This marks a deadheading, so meaning that there is no much load in it. And then from F, it has to it reach at 11 p.m. at day 2. It has to wait till day 3 4 a.m. and then it get a connection back to A. So this is actually comes into our premise like a mathematical model, like where if I'm picking this trip along with this trip, I can see that there are like, you know, a few hours of waiting and there is a deadheading. So now I have to make a decision, like, you know, which is better. Even this one I can connect with some other trips which is from E, but it might be after 4 or 5 days or maybe 2 days. That means for 2 days my truck will be blocked at E. So that is one decision, whether I should wait for 2 days and connect it with a trip from E, or I deadhead to F, and from the I wait only for 2 hours, not 2 hours, I think it is around for 5 hours, right? So I wait for 5 hours and get a trip back to A. So these are like the decisions on the go a person has to take. The manager has to take a decision. So his or her aim will be like the truck which started from A has to return back to A. So there are many choices. So which choice has to be taken? So it's a logical problem, right? So either she can wait at E for 1 day or 2 day and find a trip back to A, or she can even drastic decision. She can decide like from E come back to A without any load. So full deadheading back. So that's a second decision, but it's a worst decision, I will say. Or these combinations. What can be a deadheading? Like if for example, if city like Kolkata and or maybe the truck is coming at Kharagpur, and I am having a trip from Kolkata or Howrah. I have a starting from Howrah, so the deadheading is just from Kharagpur to Howrah. So I can live with it. So it's like a very short duration which I can go. So these combinations, how to decide. So here, limited number of trips, it's pretty easier. But if you say if you have like 10,000, 20,000 trips, it is pretty difficult to actually manage to find. And if you use other techniques like machine learning also, you have to train the network. You have to train like similarly if the trucks which have came at city E, how it was getting connected, what was the pattern, then recognize and get a decision, or like TensorFlow networks. So there are other methods, but optimization promises very good solutions. I can say it for us. We got a near optimal solution. I think it was close to 1% of optimality gap. So optimality gap is basically um, it is something which we define like what is the what is your solution from the mathematically mm, best solution. So we call it as a relaxed solution. So you cannot actually achieve anything better than that. So mathematically we can prove it. Like it is the ultimate savings or this ultimate solution what you can find, and your solution how far it is so that it can be as a percentage. So you can say that you can mathematically prove that your solution how good your solution is. So we were able to achieve like around 4 to 5% within that, which is like fairly good. And the machine learning models was, I think it was the order of 15 to 20, and it was case to case. So we had another approach where we feeded in the initial solution from the machine learning models and we improved it. That's also is there. But that's a variant of the problem. But again, moving on, you can see another trip combination, which is blue one. It will goes to B, it will go to city C, it returns back to A, and deadhead back to B. So the combinations of whether deadheading has to be the, weighting has to be the, so those become many kind of a challenges for this class of problem. So and the basic cost or the objective, we can say like the number of vehicles used, we have to reduce it. So we we took it as a fixed cost. I will come to that, like why number of vehicles and fixed cost was related. And then there was operational cost, which was a variable cost, and the deadheading penalty cost. So number of vehicles and fixed cost, because for every vehicle there is some fixed cost we have to actually invest on it. And at the same time, when you consider a continuous scheduling, say for example, I have a route set for 5 days, and this 5 days, like if I'm starting the workload on day one, that workload is going to come back at the same place after 5 days. So in a continuous scheduling environment, say like every trip repeat itself every single day, 7 days a week, then you want 5 vehicles to actually operate this particular route set. Meaning that the one vehicle will start on day one, the second, and day one the vehicle starts, it will actually return back on day 6th, and the second vehicle which starts on day 2, it will return back on day 7. So with 5 vehicles, I can actually have this trip operated, this route set operated for unlimited period of time, unless otherwise there's a demand change or the trip change, it is going to be the same. So we actually calculated the length of the route set. Actually, the length of the route set gives us the number of vehicles which we needed for that. So the fixed cost is always related to the length of the route as well. So that's a speciality when in this particular problem that we will see in the next slides. Uh, is there any doubts or clarifications so far? Or any clarifications required? Or can I move on?
Uh, Thank you, Dr. Suman. That
Yes.
you were discussing about the best route. So I have a queries like whether it is related with the what we have calculated or learned, like critical path method. Is it something related with this one in this slide? That
So critical path method, of course, that's in the project management. But if you see in the papers also, like I think it is multi-resource research project scheduling, it has been modeled as vehicle scheduling models as well. So it is basically, it is not critical path method per se, but you can relate the problem in similar lines if you want. So that's something which we also did here, even though it was a worker. So if you see the class of the problem is worker scheduling problem, but we can reduce it into different class of problems. So in this problem, we handled it as like a multi-depot worker routing problem. It can be actually transferred to a resource allocation problem and considered as a project management problem, and which will come under critical path method and in that dynamic programming. So critical path method is one kind of dynamic programming domain. So you can actually approximate into that domain as well. But I haven't worked on those lines, so I cannot say that whether it will result you with a solution or a good solution. But critical path method, if you have seen the project management which uses linear programming, that can be approximated for this. There can be approximations. You can actually consider this as an activity from A to E. It's an activity, and then considering all the trips as an activity, and then the waiting period, then you can actually approximate it and get another solution for it. But one problem with critical path method or the class, the size of the problems which are handled will be very different, because here we will be actually handling like 10,000 to 20,000 trips. So the size it's also quite different. But yeah, it can be related, but not exactly the same, I can say.
Okay, thank you. Continue.
Yeah. So moving on. So as Professor just mentioned about critical path in the project management domain, that was our approach also. We were actually thinking about like tackling this problem through vocal scheduling problems, like vocal scheduling literature. It had its own challenges, and it was already been placed. I mean, it was already there. Other people were doing it, and it was not handling such large classes of problem. So then we thought about how can we handle it in a different domain? Like, can we actually consider or like can we actually approximate it in a different domain? That's how we came into vocal, vocal depot problems. So okay, this is literature review. So I will just say we transferred it into a multi-depot vocal routing problem. But before that, we actually gone through some of the multi-depot vocal scheduling problems. Can we handle it in the classical way, which is already been in the literature? We considered like minimum cost models, network flow models, and then we actually tried it out with whatever it was available at that time in the literature. I think I remember Cedar, these two models we tried it out. We had some airline literature, the fleet assignment models. So these are all having the very similar lines and similar applications. So fleet assignment models, I can say it is instead of trucks, it was practically the airline. Like the aircrafts and how you will actually assign between different subfleets. So it was done by Cynthia Bernard, and it was a very good model. But the problem with that model for like using that for us, because deadheadings won't happen that much in aircrafts. So you can see aircrafts, it won't travel empty. They will because the deadheading, the way they handle the deadheading is completely different from a how a parcel delivery company handles it. So there were differences, but still we found that it was not adequate for our model. But we used the integrated schedule design how they used in that particular paper for our model, which actually we used in the schedule allocation. But as I said, like diverse our approach into different domains where we can find some other class of problems fitting for our application. Maybe some approximation, but can we fit it? So with vocal depot, multi-depot vocal routing problem, it is like a simple approximation, or like it's a simple way of handling this problem. Like so the standard method, it was like using multi-commodity based models, and it was not matching for our specific constraints. So we redesigned the problem as a multi-depot vocal routing problem. And how that redesign happened is the load on each of the route or the trip was considered as the demand data for that given period of time. So we consider the entire trip. So we changed the trip into a single node. So routes were actually converted into nodes, and as depots. So generally in VRP, the locations becomes a node. So instead of that, we consider the entire route as a single node, and then for every route there will be a load it will be carrying. So we computed that as the demand for that particular node, and as we know, like what will be the ETD. because at every estimated departure time, a particular vehicle has to serve that particular trip. So we already know when that trip is going to start. So now, since you have the fixed departure time, you can actually compute the time between two nodes. Like it will be first the duration of the node. There is a waiting time, because the waiting time is also we can estimate, because we know like one trip is going to end. So for example, in the graph, I know this trip is going to end at 8 p.m. So if this trip ends at 8 p.m., I know if it want to be connected to this particular trip, this orange trip, it has to wait for 3 hours. So it is like at every point we know like when the other trip is going to start. So we can actually construct a time graph according to that. So every node, how much time it will take to connect to another node, and the deadheading, everything. So these are all deterministic values which we can actually calculate before that. And we approximated the loading and unloading time at the depot. So at the warehouse. So we actually calculated that, and we predetermined the time graph. And the cost, as I said, there will be a fixed cost, and the fixed cost is associated to the number of days. So it's a complicated function, if I can say. It's not linear, because we have to consider what will be the number of days, which is again another variable, and then based on that it will be the cost, and it was computed in a nonlinear way. And variable cost is the typical variable cost, the distance and the deadheading with the penalty into the variable cost. So that will be the variable cost component and the fixed cost component. But fixed cost will be depending on the number of days of the route, and the variable cost will be mostly on the distance of the route set. So then we got like, so why we consider like this is because now the problem completely got shifted from vehicle scheduling domain to vehicle depot or the vehicle routing problem, because it has nodes, it has time between each node. So we got a time graph, we can get a cost graph. We know from every point to every point what will be the cost it will incur, because we can actually pre-calculate, and we will have a cost graph. So cost graph also is
Someone, may
possible.
I put a query here? May I
Yes,
put a query here? See, the thing is that you are located in Germany, right?
yes.
So now you are doing it for the entire world. Your network is in the entire world. Is that so? Right? Look,
Yes, yes.
yeah. So just a query. I need a clarification. I do not know
Yeah.
that. That's why. Say the airlines has a network which is from a point to point, but when you are saying the last mile, it may be not airlines but some other logistics, maybe under Lufthansa or maybe under some other subcontractor. I mean, is
Okay.
my understanding
Yeah.
right?
Yeah. Yes, yes, yes,
Then,
yes, yes.
then, are you calling that as heterogeneous because it is airlines and those subcontractors or collaborators or associates? I do not know what you call it. Those
So,
associates who are doing the last mile thing.
Professor, I would like to correct you here,
Ha.
because we are talking about two different applications here. Whatever
Hmm.
I'm discussing here is a vehicle scheduling problem, which we did with a Delivery, which is a parcel delivery company, not with Lufthansa.
Okay.
So this
Okay.
is
Okay.
basically a plastic delivery. And the other thing which you have mentioned,
Huh.
that's in airlines, and that's called code sharing.
Okay.
So,
Yeah.
for example, Lufthansa have code sharing agreements with Air India in India, but it's a
Oh, acha,
totally
acha. That is
different
no, Star Airlines.
alliance, Star
Star Alliance.
Alliance.
Yes. 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 Star
Yes,
Alliance.
yes. So,
Okay.
so Star
Okay.
Alliance
Huh.
members have the code sharing agreements, and
Huh.
like in India, Lufthansa will be having code sharing agreements with Air India,
Hmm.
and like each domains, like it will be different with Singapore Airlines in Singapore and with Thai. So that's a completely different
Okay. So
story. But we can
you
discuss about it. But that's also very interesting problem, to be frank,
okay. Okay. Okay.
because
No, no, I
but
understand. I can understand. I thought that okay. I thought that somewhere it is connected somewhere. So that's why the clarification is
yes, yes. So
okay.
this is
Fine. Fine.
in the schedule. Okay.
Okay. Okay. Fine. Fine.
So then, so the achievement over here was like we reduced the problem into multi-depot vocal routing problem, and then all the standard constraints, the standard one which is available that we used, And then we had some specific for the problem, which is like every root set, the maximum load carried in the root set should be matching with the vehicle being assigned and the vehicle. So for example, sometimes the load is like say around 600 cubic feet weight. We have that measure cubic feet, and then so 600 cubic feet we can have a smaller like Tata 407 or something. But if this 600 cubic feet you have to transfer between Delhi and Kolkata, nobody want to have a Tata 407 carrying it from Kolkata to Delhi. So for that, you should have minimum a 24 feeter, because 24 feeter is like kind of a normal truck because it has traveling lot more distance. So there are two logic for this. One is like smaller vehicles, the maintenance will be different from a larger vehicle, and the larger vehicle, even though it's less utilized, you may have to have such vehicle for those longer routes. So maximum load and the distance covered become the criteria of selection of the vehicle. And the route set duration, we have set it like it has to be multiples of 24 hours, because number of vehicles will be determined based on that. So that is another constraint. And then deadheadings, so there has to be limitation of deadheading. So one of the criteria from the company side was like deadheading had to be maximum of one in one particular route set. It shouldn't happen that one vehicle will be having more than one deadheading, and that one deadheading itself, it has to be minimal. So zero, if that's the best case. In the unavoidable situations, at least one. We cannot actually go more than that. And there is a route set duration. So I believe it was 15 days or 20 days, because beyond 20 days, if a truck is operating, it will be having mandatory maintenance. So within 20 days, it has to return back to its base location for the maintenance and other activities. So that was the duration limit. But please consider this is the limit for the truck, not for the driver. So for the driver, it will be like 3 days or 4 days, and afterwards the driver will be switching. So that comes into the driver, like it's a crew rostering problem in airlines, but it's like a driver allocation problem, I can say. So that is again a driver planning model which we did over this particular model. But that is for some other day, but not for today. But just to give you a rough idea, the primary data which we tested, because this is part of a presentation which we did internally. So I showed them the routes and how it operated. So we consider around like 1,000 routes there, and there are 11 vehicle types of different distinct size and cost structure were considered. And the next is the demand of the route. So again, determining the demand of the route, we know we can estimate the monthly load, but from the monthly load, if you take an average, that won't be a good estimate. So we use a fixed percentile of that, which is also not a accurate approach. Later on, we replaced it with a stochastic approach where we actually used scenario-based modeling, the scenario tree modeling, to identify like what can be a best scenario of representation of the load. So we started on with a fixed percentile, and later on the solution actually grew like it can actually handle the stochastic demands. So we had a Coppola method for actually estimating the how to transfer the monthly load to good estimation of a scenario tree, and we later on we used it. And then the minimum, as I said, like the demand on the route also is one of the criteria for finding out the minimum size of the vehicle. Then the fixed cost, we had to estimate the driver cost, insurance, depreciation cost of the vehicle, future scrap value of the vehicle also. That was another point. So this itself took around 2 months or so. So just to estimate like what it is. So it required many analysis, machine learning tools were used just to understand, like, to estimate what can be a good cost value we can actually give to the model, because the solution from the model, the accuracy or the worth of the solution actually depends on the data which we provide. So we had to invest a lot of time to actually get the accurate data. So this will be becoming the part of the fixed cost. And then we use Taboo search. So Taboo search algorithm, we actually didn't code it from scratch. Google OR already was providing it. We just used the Taboo search module of the Google OR. And then the large data instances was not a big issue for Taboo search. And then the existing route configuration was used as an initial solution. So at that time when we designed it, we used the existing configuration and then existing route set, which was on ground. Later on, we modified it with machine learning models, which actually had the forecasting models built into it. So it gave us a good route sets to start with. And these good route sets were actually optimized further by using Tableau search. So, so I think the people who has already worked in heuristic knows, like, if you get a very good solution, that is, even multiple good solutions are pretty good for Tableau search. That's good candidate solutions, and that it will help it to aid it to actually improve it further. So that we used, and we set around like 6 hours. We set around like 6 hours for the runtime, and then like additional constraints included computing complete duration, the discrete number of days. So this was kind of pretty straightforward in a in a mathematical model. Like, you just want to put a particular cover constraint. That's straightforward. But in Tableau search, it is like you have to estimate what will be the next closest integer, and in a standard solver of Google over, it was not available. So we had to take the source code of Tableau search, which was used in Google over. We had to modify it a little bit, and so that we can cater to our particular constraints in this case. But just to give you a glimpse, so I purposefully didn't included the mathematical model or any further analysis on that because it's copyrighted. But I can show you some estimated numbers what we got at the finally. So here it's a sample one for, I think it's starting from Mumbai, and then you can see it is for a 24-feet truck. You can see the routes that been generated, and the red one is actually the deadheading. It had a deadheading from Surat to Sarvana. So the thing was, like, usually these deadheadings, or like, the decisions which was given by our model was not being estimated by the managers on ground, because the word locations were deadheading. People may see like why we want to have a deadheading in such locations, but the overall cost was reduced. So we were able to show them with data, like what can be the reduction or the savings what we can achieve if we have a deadheading over. So sometimes deadheadings from Surat to Sevna, if you only look from 24-feet truck for this route set, it may feel like why we want to travel that much deadhead. But it might be useful because the truck might be reaching back to Delhi sooner, and it can actually have another route set connected to it, which can take it up, so that like the overall savings can be attained. So total around 23.3% of reduction on the number of routes that we were able to get. So one thing we found was, like, there were many manual corrections done by the managers, that the number of route sets was like going higher. So the route set can be something like Delhi Kolkata. So we saw that there will be like 5 Delhi Kolkata route sets, but instead of that, we reduced it to like 3 Delhi Kolkata route set, and then the other 2 route sets will be like from Delhi, Kanpur, Lucknow, Kolkata, or like Delhi, Indore, Kolkata. It might not have crossed the mind of a person who will be in charge of only the north zone, planning in the north zone. He or she may not think about the other combinations. So this actually gave a bird's eye view, like considering everything together, and to get a better savings and, like, a combined goal, I can say. So savings was around 11%, and there was around 9% overall number of vehicle reduction we were. So 9% was, I cannot actually give you the number of vehicles, but it was a large number, because each percentage in a company scale, it is a huge number. I can tell you that the success of this project was pretty good, that we decided to start an OVA division, because when I joined we didn't had an operations research division, and there were plans to, of course, but we got approvals because, like, very promising result actually came. We got Gurobi subscription. I know for academicians, Gurobi is pretty free, but for us, Gurobi is a commercial solver. So for a company to afford it, we want to show that that much amount of savings can be obtained. So this was one of the model which paid way to it, because here we only see the outsets being from generated with Tableau search, but later on there was a Gurobi model which we built. It was like a mathematical model we built for the scheduling. So overall, it actually paid way for more investing in OR division, or like investing in mathematical tools. So this was my first case study. If there is any clarification required, we can have, or else I can move to the next one. So these are the references. If there is anything, I can stop here and then we can move to the next one. If any questions, clarifications, or anything. Okay, I will take it as a go. So I will just move to my second case study. So it is in warehousing. It is a smaller case study. It's basically we saw like how in intermediate processing centers, like we have to sort these parcels. We want to know what is the next transfer center for these packages. So the book which you ordered from Delhi, it will be first sorted to say Kanpur or next to Lucknow. So for that, you want to actually process this, and for that we actually use sorters, large scale sorters for sorting these many shipments. So that is what this case study actually occurred, and there is an interesting backstory to it. I will come to that. So like this is the same picture which I shown for life cycle of a package. It starts from the pickup center, it goes to the destination center. And in all these IPCs, there will be bagging and rebagging. So we call it bagging and rebagging is because like from original IPC, I can create a bag directly to the destination. So from Delhi, a single bag which contains your book directly to Kolkata. And so that is kind of like how agile your network is. I mean, for example, now we have same day delivery. For same day delivery to exist, it has to be like direct connections. So if you want to have the book within a day from Delhi, pack it into a bag directly from Delhi airport, go to I think I forgot the name of airport in Kolkata, but Dum Airport, I don't know. Yeah, but directly from Delhi to
Netaji Subhas, are you saying Netaji Subhas Airport?
yeah, like
Netaji Subhas International Airport. That is the Damdam Airport.
Yes.
And
So like
Netaji Subhas
this,
International Airport, that is.
okay. So because it was long time back, I visited Kolkata,
Yeah,
but
of course,
yes.
of course. Yeah. Because
So
you were
yeah,
in
so
Kharagpur, IIT Kharagpur, right?
I was in IIT Bombay, but
Acha.
I have visited IIT Kharagpur a couple of times because
Yeah.
we had in after joining delivery, we started a small research initiative with IIT Kharagpur with Professor Deb. Uh, I think professor name was Gaurav, yeah, Professor Gaurav, with the Industrial and Systems Engineering Division over there. So we had good
That's why
associations.
I heard that you stayed at Kharagpur for a while.
Yes, I was the
So you
Kharagpur, and
had the
even
occasion to travel through the airport.
yes, and we
That is
hired from the
Netaji Subhas Airport.
yes. Yeah, and we hired from IIT Kharagpur also. I mean,
Yeah.
our initial team members were from IIT Kharagpur Industrial Engineering
Okay.
Department. Yeah, so these were the processing centers, and we will actually decide like what can be the next NTCs. So this bagging and rebagging is a constant process. So that's where the sorting came into picture. And just to give you a perspective, like we call something called pure bagging, like if it is directly sent to the final dispatcher, and then there will be mixed bagging, where it's basically intermediate. If it has intermediate centers, there's mixed bagging. And just like that time, it was around 3,000 dispatch centers, and direct connecting is not possible. So we have to consolidate them. And for smaller centers, it was done manually, but for larger centers, there has to be automatic sorters. So when I started, automatic sorters was like less in number because huge investment was required. But later on, we had another sorter location problem, like overall, we have to actually have these sorters so that it will be more economically, global economically. So then manual sorting has been completely removed. But in automated sorters also, some manual interventions were required. So that is where this problem originated. So maybe I can show you a picture. Yeah, so in the background, you can see this is like a Falcon sorter. The name is written Falcon sorter. So it's like an international company which actually provides very good sorting machines. So here we primarily, it's a mixture of both, automatic sorting and manual sorting at the same time. So we can divide it into a primary sorting and the secondary sorting. So the primary sorting is basically the shipment will moves over the conveyor, through the trace, and I think you can. What happened to my laser pointer? It's very slow. Okay, maybe. Yeah. So here you can see this conveyor belt. That is the primary sorting. So there is a CPU or like a central processing unit which actually controls the entire operations, and it will say like, okay, now the primary sorting is done and which all tilted trays it has to go through. So these packages will go through different tilted trays, and there are operators on the either sides. As you can see here, they will be collecting these packages which has been sorted, and they have to arrange it in this rack, which is like called as like a PTL bay. So each of these packages coming to each of these bays, so this is called as a bay, they have to sort it into different PTLs. So PTL is nothing but it's like a postcode. So you will get these packages over here, and he or she who is employed over here, they have to actually take these packages, sort it into this track over here. So at that time, this operation was not automated. So one person has to do this continuously, and it was a shift system. So how this problem, or the backstory which I told I will explain, was it all started with a worker problem. Like some workers were getting more packages and they have to work rigorously, and some others were like chill, like there was no that much packages coming over there. It was all depending on number of PTLs being assigned to this track. So for example, if you are working at a place like in Howrah and you are getting like many packages which has to be delivered within the city, you have to work almost like, if it's an 8-hour shift, you have to work entire 8-hour shift. Like there won't be any that much break for you, because you have to fill all those pin codes, and you have heavily loaded pin codes. But at the same time, your neighboring worker, there might be some pin codes which is like little far outside of the city, and there are not that many packages. For him or her, it will be like less work, because they just want to load it and they can go for a tea break and it'll be more free. So if one, and but the pay structure for both of them are the same. So for one worker, it will be like very demotivating. For the other worker, it can be like, it's okay. It is like it's a perk of his or work. So then there was always questioning between these workers. They were actually complaining to the managers. Then the managers will be like, okay, we'll shift some PTLs from here to here so that like the work is uniform. But the problem with this manual shifting of PTLs is like it is not coordinated. So it might resolve the problem for these two guys for one day, but for next day, it might even change. And the worst case, it can happen to many of the other employees. And you can see it is a very big system, and there are like lot of, so for automated sorters like in Howrah and all, it will be like huge problem. So for one or two managers to handle that and allocate the PTLs become very difficult. And it becomes so difficult that there was many issues reported that the management has to actually intervene. So that's what the backstory of this problem occurred. And at that time, my manager told like, can we actually design a mathematical model for it? So it turns out the problem or the model which was required is very simple. We just want to have an assignment. We just want to assign like the packages to different base, and each base is like having around a limit of 20 PTLs. So it's basically I have to decide which PTL depending on the load. So I have to uniformly distribute the PTLs across these shelves, I can say across these shelves, so that like uniform work will be given to different uh, employees who is working on those base. So generally like uniform load over the base. So that was the objective. So here the process is just been decided, like the first primary sorting is like moves to the conveyor and folds to the tilting trays to the casket placed in each bay, and then each bag has a destination allocated to the shipment. And the secondary sorting, the person has to actually scan it manually and then hand it over to the shelves. And here, if you see, always there is spikes. There will be spikes and okay, got stuck. Yeah, always there will be spikes in the shipments. Like there will be like higher demands, there will be lower demands, and then we have to actually readjust. And this is the story which I have actually told. So then we have to do something called as bay balancing. It's a reshuffling the bag destinations, like the PTLs, which is associated to each bay. So the objective, to put it in a word, it was like to automate the bay balancing activity by minimizing the differences of shipment across all the bays. So simple, directly like that. So if you see, the approach was like we calculated the average load per bay. So you know the total number of shipments. You know there is like, say here it will be having around 20 to 30 bays, and totally we have like around 20,000 square cubic feet of load, or like number of shipments, like 20,000 shipments. Then just calculate the average. What can be the average at each of the bays? So achieving that average is the best case now. So if all the base, if there is 30 base, all 30 base has like around an average of around 50 packages, then that's the best case. Like everybody will have equal work, but it may not happen always. So, but the difference has to be minimized. So it is something very similar to the square, square error. Like you have to minimize the square error. So which is popularly done in regression. You can see that you tends to minimize that error. We just try to do it mathematically with mathematical models, and it was very faster also. We actually created a MILP model and even open solver. We at that time we used skip models. It was pretty faster to solve it. So here the aim was unique assignment of PTLs to the bay. Total assignments of PTL has to be less than its capacity, and there should not be many deviations from the existing assignment. So this was actually an input from the managers on ground. So they don't want to rapidly change. So that is another aspect. Like if we are going to give a solution saying that you have to make like 1,000 changes of PTL, it won't be possible for a manager to do it every day or like every 6 hours or every 8 hours in the shift. So our solution should be in a way that it should be user friendly as well. So the number of reassignments what the manager has to do has to be less. The load on each of the bay has to be much closer to the average. And so our objective was we minimize this deviation of the bay load, which we make it much closer to the average load per bay. So it was simple MILP model. I will just show you how it reflected the result, because I cannot show you the exact numbers, but as you can see, two Falcon sorters, like sorter 7 and sorter 16. So you can see the orange one was before. You can see the deviations in the load, and the base is like there was around 65 base. So 65 base means like each of the bay had around 1%, so 1 or 2%. So it will be like 65 or like 130 workers working in one sorter, in sorter 16. And you can see like for here the person who is working at 41 bay, he or she has to handle this much peak load. Like they will be fully busy, but at the same time you can actually consider somebody like working over here, which is like in 53, they don't have much load. So after the model you can see these small spikes. So the direct line which you see, that is the average one, but you can see this small one, this is green color. You can, if you can see in my pointer where it is, so that was the result from our solver. So it is having variations, of course, because the peak load is like that, so there is variations, but moreover it was uniform. Nobody had to work this peak loads, and nobody has to work like peak lows as well. Like there is no low and there is no that much high. So moreover, closer to the average, we were able to get the load balanced. In sorter 7, you can see like our solution was kind of very close to the average. Like the blue line and the green line is kind of the same. So our solution was very close to the average. And before implementing our model, this was the variation. So this sorter 16 and 7, you should understand it is not in the same location. This might be maybe in the south, this might be in the north. It depends on the, it depends on the location and the load variation. But you can see how much different it was. Just imagine like this much high peaks were actually happening. So workers were actually working on very different load arrangements. I mean, their workloads was like drastically shifted between one bay to another bay. So now after the model, it became more uniform and the people were more satisfied. Like at least it is not about how much load one person is actually working on. It's if it is uniform, everyone is happy. If one person is working too much, if the other person is not working that much, it creates disputes. So this solution was very much helpful for the managers on the ground, so that they were able to actually mitigate this situation, and it was automated. It's like every day they will get a report like, okay, you have to change this numbers, this many numbers of PTLs, and like this PTL right now it is in this particular shelf, you have to change it from this position to that position. So it was like very direct point to point changes, and you have to see like there was a limitation on number of changes which can be done by the solver, right? So as I have mentioned, so there shouldn't be too many deviations for the manager. So that was also an input parameter. So 20, 30 changes, that's a maximum they can do in a shift for a manager. So that also was incorporated. So this much amount of smoothness in the bay allocation, bay load allocation, we were able to achieve. So this is my second case, and these are the following some of the sorting operations we did. And I mean, some of the papers we actually referred to design the model, but it was a fairly small mathematical model, but the implication of the model was huge. So yeah, so this was my second use case. So if there is any queries, we can take it now, or we can move to our third case studies. So if there is any clarification, discussions we can have, or else we can move to the next one. Okay, I will take it as an S. I will just move to the next case study. So my first two case studies was in parcel delivery company. It was primarily in logistic, in like their parcel delivery logistics, I can say, trucking and warehousing domain. But now this is where I'm working. I'm working in aviation now, and mathematical models in aviation. So in this case, we will actually consider a tail assignment problem, and that too in seamless maintenance period. So seamless maintenance period is basically 7 days from day of operation. So day of operation, say consider today is the day of operation. So 7 days from now, it is something called as ops master period. It is like operations master period. So that time it is considered differently, and tail assignment happening after this day of operations plus 7 days till day of operations of 60 days. Excuse me,
This
till 60
aviation,
days.
this aviation case study, I mean,
Yeah,
I believe, since we have to close at 7:30, it can be a bit compact. So you look at
it
your
is,
time.
yes.
Yeah. Okay.
Yeah, it is. It is like I think only 6 slides, so it's very compact.
Okay. I mean, yeah.
Yes. So I just the same way I'm just giving an introduction to the airline's workflow. So we start with a market analysis, and I just gave the name of the softwares also we actually use, which is kind of like it's a flagship softwares which we actually use in Lufthansa, and it's part of Lufthansa itself. So for demand forecast, we use something called Netline Plan. So we just want to know like what is the overall demand, like who want to fly from which location to which location, and this demand actually. So for example, the demand of people who wish to travel from say Mumbai to Frankfurt, or like from Bangalore to Frankfurt, we actually forecast it. So that will start with a market analysis. Then there is a big step called slot planning. So slot planning is something like at every airports, the airlines actually has to negotiate, has to bid. Actually, it's a bidding process for the slots. So for example, if I want to get slot in Mumbai in the morning session on a Monday, it is very hard because it's a key slot and people really want to buy it, and the bid will go for millions of dollars. And there's a popular case with ANA Airlines. ANA Airlines from Japan, actually, they acquired another company just to get favorable slot as a Tokyo airport. So the only aim was to get good slot at a particular airport. They actually acquired that company. So getting the slot is kind of a primary objective. I mean, that's kind of the first step, like long-term planning, like for an airline. So slot planning, and it's pretty famous, like the slot arrangements in Luton Heathrow Airport. It is one of the highest bidded slots. So where sorry, the when the aircraft has to land. So that slots planning, we use something called Netline Plan, which airlines pretty much do like way ahead in the future. Like now the discussions will be going on like the slot planning for 5 years or 6 years. And especially when the new airports are open. So as a case like Guragaon, there is a new airport which is being opened. Traditionally, it was only the Delhi International Indira Gandhi Airport, but now there is a new airport being opened. So the slot planning, like I think it might be already been sold by now, but so that's very long time planning. And then there is route development and scheduling. So there is origin destination pairs. We have to determine what will be the frequency. So route development, it's very similar to the network problem. We have to see what can be the popular origins and destinations, and how many flights we have to actually cover these origin and destination points, the flight frequencies. Then network scheduling will come. What can be the hubs? So, for example, Air India has Delhi as its hub. Lufthansa has Frankfurt and Munich as its hubs. And for example, there can be diverse, like for example, Finnair has hubs in Helsinki. They have arrangements with Doha in collaboration with Qatar Airways, and then they have hubs which is located in Sydney uh, with Qantas, Air Qantas. So it's basically hub design. So where and all I have to actually plan my hubs. So that will come in the network scheduling stage. So there is hub design, or it can be point-to-point flight. For example, like Air India Express, they have point-to-point flights. They have multiple. So it's not like multiple hubs. Their aircrafts will kind of start from like different locations. It move to different point to point and return back to its originating point. So it is kind of two different branches. There's like hub and spoke and the point to point. So network scheduling actually decide like, what can be the popular hubs, or if it is a point to point, what can be the popular points we have to actually consider. And then there is timetabling, and this has to be done long before so that like it can be sold to the customers. Like they should know when those trips will be, or when those flights will be actually scheduled. So timetabling will come into that. And then this one is practically the planning, which can happen in long term. Then comes the fleet planning, which is more kind of operational. We decide on what
So,
type of
so,
aircraft.
so
Yes.
Dr. Suman, sorry for interaction. Just you have only 4 minutes. Just to hear just an okay.
Okay, it's
7.
1:30, 10 minutes. Okay, it's
Yeah,
4 minutes. Okay.
4 minutes.
Okay, fine. So it's basically like we have fleet planning, we have crew planning, maintenance, airline routing, and tail assignment. So I will just jump to tail assignment. So it's pretty much like what all we consider in tail assignment is basically we want to consider like the fuel efficiency. So tail assignment is basically a registration of the aircraft, which we have to actually assign it for different different flights. So it will be having aircraft specific restrictions like APU INOPS. So it's basically the auxiliary power unit. So you can see like some airports will have it, some airports may not. So if I am actually making an aircraft going to an airport which doesn't have APU support, I mean, it doesn't have a ground GPU support, then the aircraft should have an APU. So it is basically at the end of the, like I have a model here. So it's something like here at this point, you can actually see an APU. It's like an alternating engine which powers the aircraft when it is on ground. So on ground, they won't actually use the main engines. They will use the APU engine at the back. So similarly, there are many restrictions like maximum takeoff weight restriction, ETOPS restrictions, ADR restrictions. So one of the classical thing with aircraft problems is like there will be a lot of restrictions, a highly constrained problem, and we have to find out a feasible solution. So it is basically like all these restrictions, like maintenance restrictions, forced connections, ground time, on-time performance, crew planning. So all we will consider, and we will actually uh, do the tail assignment. We'll assign a registration to certain tail. So earlier in the business, they had calibration models which used LIFO, FIFO, which was simple workflow. But this was kind of what people were using. And then normalizing weight and all, the user has to give a lot of inputs. Then we came up with something called as hierarchical optimization. So it was like it was already there in the team, and it actually automated the workflow for the customer. They just have presetted hierarchies they have to say, and then it was automated in that end. And it's just like what innovation we bought was like we combined time space network with with connection network. So these are like popular network which is already in the literature, like there's airport network, there is route network, where there is time, space, and connection. And this is a very good paper for that. It's a good paper in airline network optimization. But we combine these two network together, and we use some innovation in the graph generation, which helped us to consider very large global graphs. But our aim was to actually have a objective-based graph generation and graph pruning we have to do. We used a REST framework for it. It's another way of handling graph building. And then there was there were some things we have to discuss, but we don't have time. But then there were long and shorter connections. We had to consider like multi-aircraft agreements, AOC agreements, leasing agreements. So considering long and shorter connections in the same graph, it was pretty difficult. So for that, we use this REST framework for graph building, and we consider like optimal solutions for so optimal solutions. I'm saying like we got mathematically proved that this is the best solution which can occur for the given customer profiles what they have set it. So for around 20 to 25K flights with 60 plus registrations under different subfleet, we were able to get optimal solutions, and we are setting them now. And I think this is my last slide. Yes, yes, yeah. So this is a workup, like, yesterday only we actually sold the new hierarchical model to one of the popular airlines in Asia. So yeah, so this is what we did with this, intelligent graph building. I can say we handled this problem, and we were able to get optimal solutions for such a large problem, I can say. So this is my last slide, and there is any questions, suggestions, I can take it now. I'm sorry for exceeding if I exceeded the time.
No problem, no problem.
No,
Just
no issue.
okay, no.
No, this has been. Am I audible? Am I audible?
Yes, yes,
This
Professor.
optimization is always very interesting area. In fact, it is such a area that it can be used in many places and many applications. So as this is done, in the area of transportation, and of course aviation is a kind of transportation overall, and logistics, transportation logistics, that's the basic coverage it was. And when it comes to industry 4.0 in this area, so these optimizations can be truly be implemented more efficaciously, I am sure, Dr. Shoman, with the help of all these network sensors, and maybe with the help of security, cyber security and all, or big data analytics also can be passed in. So to the modern applications are not isolated. They are all, I would say, in tandem or in sync. Hence, in a large manufacturing company, the manufacturing per se will always be having the logistics aspect to it, both upstream and downstream. So this, I think, that way, Dr. Shoman, it has been very helpful, the optimization insight into this. It was a very nice to hear the several case studies, which is very, very realistic and which is very real world issues. Thank you for accepting our invitation and speaking here. Professor Roy, I believe, will be formally closing, and Professor Kundu, I believe, will be reminding the or telling the participants about the question bank and all.
So thank you, sir. So it is a wonderful session. I think
Sir,
everyone has.
One question, sir. I am asking Pulendu. You have changed the question bank. So I have already made the answers. So when can we have to provide it?
No. Tomorrow the test will be happening. Tomorrow the test time is given. It is actually tomorrow is the test. It is a question bank so that you can get ready. We have given it in advance so that you can prepare.
Already I have made the answers. no problem. So
That's
that's why
very
I'm just
good.
asking now.
Excellent,
Ah.
excellent, Professor
Excellent.
Mondal. That's great to know. I mean, I believe the
Already
others
I
are
have
doing that also. Wonderful,
Ah.
wonderful.
430 I got, within 5 I completed that chapter.
Oh, lovely. That's so
Lovely.
nice to hear. Great, great, great.
Okay, sir.
So thank you. So we have next section. So I am requesting all the participants to log into the next session. Thank you.
Okay, thank you everyone. I also have given the feedback link at the chat box. Please fill out the link before joining the next session. And I also have shared the question bank for the tomorrow exam slot in the WhatsApp group. Everyone download it and solve it accordingly. Thank you very much.
Yeah, thank you all. Thank you all for your time. And yeah, wishing you
Thank you very much,
all you guys
Dr. Shom.
the very luck.
Yeah.
Yeah. Bye bye. Thank you. Thank you for
Bye
having me.
bye. Bye bye. Bye bye.
Okay, then I'm closing the session.